Okay, good morning. Welcome to the third day of APLAS and ATVA in Kyoto. This morning we start with a joint keynote talk given by Professor Naoki Kobayashi at the University of Tokyo. So let me introduce the speaker just briefly. Naoki was born in 1968 and he did all the studies, the bachelor, master, and PhD at the University of Tokyo under the supervision of Aki Yonezawa, who is actually in the audience. And he's now a professor at the Department of Computer Science at the University of Tokyo. So he gave many invited talks and he served many conferences as the PC chair, such as FOSAX this year, FSCD 21, LIX 20, ICAP 15, and so on. So and his influence, especially in nurturing students, is widespread. You'll be surprised to know how many students and students of Naoki's are in the audience. Probably more than 10, 20. Yeah. Then, if I can add a little bit of personal touch. So I think there are two things that are very interesting in theoretical computer science. One is fixed point logic, and the other one is this complicated dynamics of higher order computation. And Naoki's work bridges these two fields, which makes his work all the more interesting. So, please.
Okay, so thanks Ichiro for the very kind introduction. So I'd like to thank the organizers of both conferences for this kind invitation. So today's talk is based on joint work with many people, including those listed here, but this list is not exhaustive. Okay, so today I'm going to give an overview of our recent project on automated program verification based on high-order fixed point logic. So it serves as a unifying framework for automated verification of high-order functional programs. So I listed some of other automated verification framework here, and ours is one of the most expressive ones in the sense that it supports high-order predicates as well as arbitrary combination of least and greatest fixed point operators. And I'll explain the importance of those features later in this talk. So in our framework, program verification problems are reduced to the validity checking problem for HFZ formulas. And this serves as an alternative to the host model checking approach, which we have been working on for more than 10 years now. So I'll also discuss this point later. And before going into details, let me give you a very quick demonstration of one of our tools developed in this project, just to give you an image about what we are aiming for. Okay. And actually, the tool has been implemented by Ryosuke Sato and Hiroki Katsura, and not by myself. Here is a web interface for our tool, which is a verifier for OCaml programs. Okay. And here is a sample input, which defines McCarthy's 91 function. And the main function asserts that the return value should be always 91, as long as the input n is no greater than 101. Okay? And the goal here is to check that assertion failures never occur. Okay. So to check that one, we just need to push this button. And then the system first transforms the program to this kind of logical formula. And you need not read this right now. So I'll explain how to read this kind of formula later. But anyway, so program verification problems is reduced to the problem of checking the validity of this logical formula. Okay? And then the tool checks automatically whether this formula is valid or not. And in this case, the tool says it is valid. Okay? So that means the program does not suffer from any assertion failures. And the tool also says outputs some certificate for the validity of the logical formula. And if we modify the program a bit, so for example, if we insert, so if we insert equal here, okay, so then this program is no longer safe. And if we push this, then the tool now says that the formula is invalid. Okay? So that means the program may suffer from assertion failures. So we have been developing these kinds of tools and the theory behind that. Okay. Sorry. So now let me explain what is high-order fixed-point logic. So HLZ is a kind of high-order logic that supports least and greatest fixed-point operators. So here is a syntax of formulas. So in addition to ordinary logical connectives, we also have least and greatest fixed-point operators. So mu x dot phi is a least predicate x such that x equals phi. Okay. So for example, mu x dot x is equivalent to false because x equals x is satisfied by any proposition, and false is the least among them. Okay? And mu x dot phi is a greatest predicate x such that x equals phi. So mu x dot x is true. So let me give you a more meaningful example. Okay. So this formula represents a least integer predicate f that satisfies this equality. Okay. And to see what this means, let us rewrite this f according to this equation, and then we get this one. Okay. And by further rewriting f, we get this kind of formula. Okay. So this is equivalent to y no less than 0. Okay. And as we will see soon, this kind of fixed point formula naturally arises from program verification problems. Okay. So let us see another example. So this is a new formula, greatest fixed point formula. This represents the greatest integer predicate f, such that this equality holds. Okay. Again, to see what this means, let us rewrite f according to the equation. Okay. So then we get this one. And by further rewriting this, we get this one. Okay. So that this is equivalent to y less than 0. Okay. So why do we care about these kinds of fixed point formulas? So that is because the semantics and specification of recursive or loop programs are defined by using fixed points, if you recall the denotational semantics of programming languages. Okay? So that properties of programs to be verified can be expressed by using fixed point formulas. So let me give you some example. Okay? So let us consider this simple recursive function f, which terminates if y equals 0, and otherwise recursive calls itself with the argument y decremented by 1. Okay? And suppose we are interested in checking the termination of this function f. Okay. Then that is expressed by this fixed point formula. And here, the predicate f means that the function f terminates for the argument y. And that is defined by this fixed point equation, because if y equals 0, then f immediately terminates. Okay? And otherwise, this recursive call should terminate. And that condition is expressed by this formula. Okay? So the termination property can be expressed by this kind of formula that mimics the structure of programs. So in this manner, by using fixed point operators, we can naturally express the various properties of programs by using fixed point formulas. And this formula says that function f terminates for any argument y. Okay? And actually, that is false in this case, because f diverges for negative argument. Okay? And if we are interested in the non-termination property instead, then that is expressed by this formula. Okay? And here, so this time, the predicate f means that the function f diverges for the argument y. Okay? And that is given by this fixed point equation, because for function f to diverge, y should not be 0. Okay? And also, this recursive call should diverge. So that's why so f is defined by this equation. Okay? And then this formula says that for some argument y, the function f diverges. Okay? So far, we have considered only first order formulas. Okay? So let me give you an example of higher order predicate. Okay? So here, this fixed point equation defines second order predicate f that satisfies this equality. Okay. And here, the first argument of f is integer argument g. Okay. So that f is a second order predicate. Okay. So to see what this means, again, let us rewrite f according to the equation. Then we get this. And by further rewriting f, we get this kind of formula. Okay? And that is equivalent to the condition that there exists u no greater than y, such that g of u holds. Okay? So why do we care this kind of higher order predicate? So that is required for modeling the semantics of higher order programs. So for example, let us consider this example. Okay? So here, the function f takes another function g. Okay? And either calls g or recursively calls itself. Okay? And then suppose that we are interested in the main termination property of the main function. Okay? Then that is expressed by this formula. So here, the predicate f means that the function f may terminate in some non-deterministic execution sequence. Okay? So here, there is a non-determinism here. Okay? So that so this formula represents that the function f may terminate for some non-deterministic execution. Okay? And then that is defined by this formula, this fixed point equation. And that is because for this to terminate, either g of y should terminate, either g of y should terminate. That is expressed by this formula. Or this recursive call should terminate. And that is expressed by this. So we can just combine them with this junction. Okay. And if we are interested in masked termination instead, okay, so then that is expressed by this formula. So here, the predicate f means that the function f must terminate in all the non-deterministic execution sequences. Okay, and then this time, this non-deterministic choice is expressed by conjunction, because now we require that both branches should terminate. And then this formula means that the main function should terminate for all the arguments y and for all the non-deterministic execution sequences. Okay. And even if we do not care about high order programs, still, even for first order programs, high order predicates are useful for modeling some control constructs or data structures. So for example, let us consider this program. Okay. So here, the function f either calls raises an exception or recursively calls itself. And the main function calls f with this exception handler. Then suppose we are interested in checking whether this assertion never fails. Then that is expressed by this kind of formula. Okay. So now here, the predicate f corresponds to, this predicate f corresponds to this function f as before. But actually now f takes additional argument, h. Okay. And that corresponds to the exception handler. So exception handler itself is represented by a predicate, so that f is second order predicate, even though the source program in the source program f is a first order function. Okay. Okay. So now, I have so far given several examples of encoding various program properties. Yeah.
So basic question before, why integer types? Couldn't you handle more expressive types?
Yeah.
Okay.
Yeah, actually, so this notation suggests that somehow logic is parameterized by basic data. And here, for the simplicity, we only consider integers.
Okay,
yeah.
Thank you.
Okay. Thank you for the question. Okay, so now let me discuss a little bit about the generally expressive power of this logic. So we have shown that it is expressive enough to encode arbitrary regular temporal properties of high-order functional programs that can be expressed by the modal calculus, which subsumes CTL or LTL or CTL star. And also, actually, it is in a sense just expressive enough to encode those properties. So we are interested in automated verification, and program verification problems are reduced to validity checking of logical formulas, so that the logic should not be too expressive. So if it is too expressive, then it is hard to construct automated tool for checking the validity of logical formulas. Okay, but so SCADA has shown that in a sense this HFZ is just expressive enough to encode these properties, and that is somehow in contrast with other logics like calculus of inductive constructions as used in proof assistance. Okay. So calculus of inductive construction is fine for interactive verification, but not for fully automated verification. So in this sense, HFZ is suitable as a generic framework for automated high-order program verification. And as long as we are concerned with these properties, so we can reduce them, all these properties to a formula of HFG, and then use a single unifying tool for checking the validity of those formulas. Okay? And you may fear that this generality may have a cost, but actually, according to our experiments, that is not necessarily the case. So here's some experimental results for automated verification of first-order programs. And here, mu2CHC is our tool. And we have compared that with the CTL verification tool by Cook and Koskinen. And as this table shows, actually, our general tool that can also support properties beyond CTL almost always outperformed their tool. And similarly, this is result for higher order program verification. And we have compared that. So here, mu HFL shown in the horizontal line is our tool. And vertical line shows previous tools for automated verification of function programs, specialized for each property, like termination or non-termination or safety property. And again, as this graph shows, for most of the instances, our tool outperformed the previous specialized tool. So our single tool outperformed the combinations of previous tools specialized for each property. Okay, so that is a good news. Okay, so now let me discuss some other approaches to automated verification of high-order programs. Let me first discuss the force model checking approach, which we have been working for more than 10 years now, and gradually switching to the logic-based approach. Okay. So actually, I've given an invited talk at APLAS 2009, which is 15 years ago. And there, I advocated the force model checking approach to automated verification. So let me explain why we are switching to high-order fixed-point logic approach. So actually, both force model checking and our current approach of HFG-based approach are, in a sense, both based on high-order extensions of finite state model checking, but two different high-order extensions. So in finite state model checking, the systems to be verified are finite state systems. And the logic to describe properties is typically modal mu calculus or subclasses of it, like LTL or CTL. So, so host model checking, in host model checking, the systems to be verified have been extended to high-order ones called high-order recursion schemes. And I do not explain detail of this one, but basically, you can think of this as a high-order recursive function programs just for generating infinite trees. Okay. So this is a sort of infinite state system, but still the model checking remains decidable. So based on that, we have developed previous, not necessarily previous, but tool called Mochi for fully automated verification of OCaml programs. But actually, there is another high-order extension, which is called HL model checking, where we can, instead of extending systems to be verified, we can extend the logic to high-order one. Okay? And that is called HL model checking, which is also decidable for with finite data type. And our current approach is, in a sense, based on this. Okay. So let me explain why we are switching from this horse model checking to H-hill model checking. So actually, there is a close relationship between horse model checking and H-hill model checking. So we have shown that horse model checking and H-hill model checking are mutually reducible in polynomial time. And we have also shown that there are natural translations from program verification problems to horse model checking and also H-hill model checking. Okay. So this itself does not justify our transition from horse model checking to H-hill model checking. But actually, if we closely look at this reduction, okay, actually, this reduction breaks down in the presence of infinite data domains like integers, lists, or trees. So the translation in this direction from horse to H-hill model checking is fine. So it works fine in the presence of infinite data domains. But the translation in the other direction breaks down when we add infinite data domains like integers. So in this sense, H-hill model checking can be considered, in a sense, a more foundational problem on which the program verification should be based. Okay. And indeed, so here is a kind of tool architecture for the horse-based approach and H-hill-based approach. And so previously we have been working on horse-based approach, and then there we have to develop various independent techniques to deal with various properties of actual functional programs. But now with H-hill-based approach, we just need to encode these different kinds of problems to HFG formulas, and then just invoke general HFG validity checker. Okay. And another reason why we prefer HFG-based approach is that it is easier to deal with non-functional features like references or concurrency, etc. So for example, let us consider this program, which uses reference cell. Okay? And in our previous horse-based approach, actually we just throw away information about these references to map the program to pure function programs, which can be directly modeled by horse. But with a logical approach, we can take a more flexible approach. So, for example, we can reduce this program verification problem to validity of this kind of formula. So here, So here, the predicate f means that the function f may return R, and the predicate x represents that reference cell x may hold n at some point. Okay? And then based on that intuition, we can approximate the safety property of this program as the validity of this logical formula, where x and f are the least predicates that satisfy these conditions. And you need not necessarily understand this formula. This may be a little bit complex. But the point is that, so here we make some abstraction on the behavior of programs on references. And that abstract semantics or approximate semantics, as used in static analysis or data flow analysis, can also be naturally expressed by using fixed points, so that we can represent them by using logical formula, fixed point logic formula. Okay. And another advantage is that it is easier so since it is based on logic, it is easier to integrate with other logic-based automated verification, like constraint horn clauses. And also, we could also integrate that approach with semi-automated verification, like verification condition generation approach or Dijkstra monads for verification of functional programs. And they are also based on certain logics, so that our logic based approach is easier to integrate with them. And also, we can possibly integrate our approach even with interactive verification, because even in interactive verification, a certain logic is used, like calculus of interactive constructions. So although the expressive power of the logic is quite different, so that it is not so easy to integrate, but it will be possible to integrate them. Okay. And let me also little bit mention refinement types approach, which is also another popular approach to automated verification of functional programs. So refinement type system has been a popular approach to free or semi-automated verification of higher order programs. And typical example is liquid types. But they are usually restricted to reason about only safety properties. And there are some work to deal with other properties, but it is typically tied to a particular programming language, so that refinement type systems need to be redesigned for the change of target languages or properties to be verified. And actually, as I'll explain later, we can actually use refinement types for validity checking of HFZ formulas. Okay, so then we just need to design a refinement type system for HFZ validity checking once and for all for various kinds of programming. So in a manner independent from programming languages and properties to be verified. So these are the points in favor of our logic-based approach. Okay, so far I hope that I have convinced you to some extent the usefulness of our approach. So, but that depends on whether we can construct reasonable, fully automated tool for checking the validity of fixed point logic formulas. Okay. So now let me explain how we can construct such a tool. Okay. So actually, we can obtain automated methods for HLZ validity checking by generalizing techniques used in program verification. So let me take example of termination verification. Okay. So so to check the termination of a given program automatically, it is now standard to first reduce it to a safety property, as pioneered by Cook and Rivalchenko with their technique of binary reachability, a reduction to binary reachability problem. And then we can use model checking or refinement types or whatever to check the safety of the resulting program, P prime. Okay. And then if the resulting program is safe, then we can conclude that the original program P is terminating. And otherwise, we go back to define the reduction to the safety property. Okay. And actually, we can use the same technique, same overall architecture, to prove the validity of a given HFZ formula. So given a HLG formula that may contain both least and greatest fixed point operators, we first remove these fixed point operators by a certain approximation to get a new HLG formula, which is a formula with only greatest fixed point formulas. Okay? So then that is easier to prove automatically. And actually, again, we can use the generalization of these techniques to check the validity of greatest fixed point formulas. And then if this phi prime is valid, then we can conclude that the original formula phi is also valid. And otherwise, we go back to refine the approximation. Okay. So let us take a closer look at this first phase, okay, by using a simple example. Okay, so let us consider this recursive function f, which I've shown before. Okay, so to check the termination property, as I said, we first reduce this to a safety property. And here, I actually use the technique of Fedkovich, sitting there, in 2018. Okay? So here, we can bound. So here, the function f is transformed to f prime. And here, we have added additional argument z, which represents an upper bound of the depth of recursive calls. Okay. And here we check that the upper bound is still positive. And then, so if upper bound is positive, then we go to simulate the body of the recursive function. So that, so if this program does not suffer from assertion failures, then that means the depth of recursion in the original function f is bounded. So that implies the termination of this original function f. Okay, so that the safety of this resulting program is a sufficient condition for the termination of the original program. Okay? And by the way, here, so for the simplicity, I have just given y plus 1 as the upper bound. But we can, by increasing this bound, we can get a more precise approximation. Okay? So we can use the same technique to deal with HFG formula. Okay? So let us consider this predicate given by this fixed point equation. And actually, this formula captures the termination property of this one. Okay. And the goal is to remove this fixed point operator and replace it with greatest fixed point formula. Okay. And we can do the same thing. So, so to check that f of y is valid for all non-negative integers y, we can first reduce it to this greatest fixed point formula. And as in the right-hand side, we have added additional parameter z. Okay. And this z represents an upper bound of the number of unfoldings of this fixed point equation. Okay. So this validity of this formula is a sufficient condition for the validity of the original problem. Okay. So here, f prime z is under approximation of the original predicate f obtained by z times unfoldings. Actually, z minus 1 unfolding, sorry. Sorry, z times. Sorry, I think this is correct. So to see that, so for example, f prime 0 is so based on this equation, f prime 0 is equivalent to this one, which is equivalent to false. And if we increase the value of z by 1, so f prime 1 is equivalent to this and this one. And if we increase z further, then we get a better approximation of the original formula. Okay. But anyway, so for any value of z, this formula gives under approximation of this, so that if this is valid, then the original formula is, so yeah.
So is this automated? Because
Yeah.
it seems that you're coming up with the ranking function somehow, right?
Yeah, so here the upper bound is fixed to this expression, but in our tool, so this is, so the coefficients of this linear, so we consider linear expressions as the upper bound, and then we gradually increase the coefficients until the, yeah, validity checking succeeds.
So in that case, if the program's termination is polynomial in the argument, you may have.
Yeah,
to
in
look
this
for-
case, yeah, it must be. Yeah, no, not necessarily. Yeah, depths of recursion must be, yeah, linear. But actually, we can also increase the number of parameters, and then we can deal with possibly non-polynomial. Yeah.
Thank you.
Okay. Thanks for the question. Okay, so in this example, actually, so I have transplanted what's going on in the termination verification to rephrase what's going on in the termination verification to the validity checking for formulas. But actually, this technique is applicable to other formulas, not necessarily coming from termination problem. Okay. So for example, we can apply the same technique to this kind of formula, combines both least and greatest fixed point operators. So you need not necessarily understand what this means, but just in case you are curious, so this formula represents the property that G is called infinitely often in this program. Okay. And by using the same technique, we get this kind of greatest fixed point formula. Okay. And that is arguably easier to prove automatically. Okay, so now let me also briefly discuss the second phase for checking the validity of greatest fixed point formulas. And the methods for checking the validity of greatest fixed point formulas can be obtained by generalizing the technique for safety property verification. And here I discuss the technique based on refinement types briefly. So, as I said before, we can actually, so refinement types is a popular approach to safety property verification. And we can actually use the same idea to check the validity of greatest fixed point formulas. And this technique has been originally invented by Barn et al. In Oxford, and we have somehow defined that technique. Okay. So here we consider types for predicates like this. So this is a type of propositions that hold whenever the condition psi holds. Okay. And this is a type of integer predicate, and this is actually dependent types, a kind of dependent types, and this is for higher order predicate. Okay. So for example, this predicate can be given this type, which says that it is a predicate on integers, and that is valid whenever the argument x is positive. Okay. And based on this intuition, we can construct a refinement type system. And then we can show that that type system is sound in the sense that whenever the proposition phi has this type, then that proposition is valid. Okay. So that the validity checking problem is reduced to a kind of refinement type checking problem. Okay. And based on these techniques, we have constructed automated validity checker for HLG formulas. And this is a graph I've shown before. So, so our tool outperformed previous tools based on the host model checking. And and other program verification and transformation techniques can also be lifted to deal with high-order fixed-point formulas. And I listed some of them. So I recommend you to take your favorite program transformation or program verification technique and see whether it can be generalized to deal with fixed-point logic formulas. Okay, so before concluding the talk, let me discuss some remaining challenges. So as I said, we have already constructed a fully automated validity checker for high-order fixed-point logic formulas, but it still has some scalability problem. So probably, so our current tool is fine for a few hundreds lines of code, but it will not scale for thousands or millions of lines of code. Okay. So to improve the scalability, there is still much work to do. And to address that, we have been trying to integrate various other approaches, including model checking and refinement types. And also, as in other automated verification, we are struggling to find good heuristics for finding invariants or auxiliary lemmas like that. And we have been recently trying to apply machine learning techniques, but unfortunately, they are still not completely satisfactory. And also, we have been recently trying to integrate our method with some form of testing. And a student of mine is going to present that work in this afternoon in APLAS session. And also, so in this talk, we have focused on pure verification of pure functional programs, but we hope to deal with other features like references and concurrency. And for references, we have already done some work to remove reference cells from programs to get the verification problems for programs using reference cells to those without references. But still, there is also much work to do for this. And also, even for pure verification of pure functional programs, so our HLG is suitable for, can deal with arbitrary regular temporal properties, but some of the properties like program equivalence cannot be fully captured by the validity checking program for HLG. So we need to go a little beyond that. And we need to develop an automated method for dealing with such properties. And actually, we have already done some work, but still, so even also in this domain, there is still much work to do. And also, as I said, we hope to integrate our automated technique with semi-automated and interactive verification. Okay, so let me conclude. I have introduced a program verification framework based on high-order fixed-point logic, which serves as an uniform foundation for automated verification. And there is a natural reduction from high-order program verification to HFZ validity checking, thanks to the expressive power of fixed points. So it supports both safety and liveness verification. And the automated methods for HFZ validity checking can be obtained by generalizing existing methods for program verification or transformation. And this is a kind of future work, but smooth integration with semi-automated or interactive verification should also be possible. Okay. So that's all. Thanks for your attention.
Questions? Actually, let me start with one. So, like, what about compositionality? Because what I really liked about your horse work was that like, all the programs have got types, right? So therefore, you can do compositional verification. What about this HFL approach?
HFZ, if we use refinement type approach, then that verification method itself is, in a sense, compositional.
So, like, do you mean that the translation from a program verification problem to an HFLZ formula is compositional as well, or is it the compositionality comes after that?
Yeah, after that, that is what I said. But if you want to make the translation also compositional, then you could specify the interface by using, for example, refinement types like that. Then, yeah, the translation itself can be made compositional. And in a sense, so I forgot to advertise our work with my student, former student. Let me see. This one. Sorry. Yeah, I forgot to advertise this work. So in a sense, so we have been recently working to study the relationship between Dijkstra monads and our approach. And there we have proposed some integration with Dijkstra monads where user can specify some interface of part of the program as by using refinement types, and then sorry, that is not exactly this one, but yeah, but as I said, yeah, it is possible to make the translation.
Let's discuss this.
Yeah.
So, like during the coffee break. Yeah, thanks.
So thank you for a nice talk. I have a couple of questions. The first question is, how do you deal with termination when you have recursive data types like trees and lists? It's pretty challenging. Do you just use like a size abstraction or?
Yeah, so the approach I've explained can be easily extended to deal with recursive data structures. So you could use, for example, size function to give an upper bound of the depth of recursion. That is one approach. And actually, yeah, we have already implemented a tool that deals with not termination, but the productivity of stream manipulating programs. And there, we used the length of this as an upper bound of the depth of recursion. Yeah.
So the other question is, it seems that you can also generate counterexamples, or did I get you can generate counterexamples?
Yes, yeah, we can generate a counterexample for a fixed point formula, but we have to translate that counterexample to that for the source program. And that part has not been implemented yet, but that should be possible.
We have some time for questions.
Can you hear me? Yeah. So in my experience, issues with, you mentioned refinement types at some point, issues with this sort of automated verification is that when there's an error, it can be pretty difficult to act upon. Like the tool tells you something's wrong, but it's very hard to know what's wrong. So I'm curious to see what kind of error messages you get in your system when it goes wrong.
Yeah, I think that is related to the question before. So we could generate a counterexample when the program does not satisfy the property.
Okay.
So could you go to the example you had where you transformed the program for termination, the let f, yeah, that example.
This one?
So what does this transformation look like when you have higher order functions?
Yeah, so if we have higher order function, then we also add another additional arguments that additional integer arguments that express information about function arguments. And then that additional argument can also be automatically inferred. Yeah.
So is it effectively an extra z per?
Yeah, yeah,
okay.
extra z, right.
I actually have a follow-up question, and it's related to like one of the earlier questions of Sriram's. So like, can you, if you can go to the next slide.
This one?
Then the next one. No, this is good, thanks. So like here, like your approach to the least fixed point operator is to like try one bound, and then if it works, then it's good, otherwise you increase it, right? So like
Yeah, increase coefficient.
try and
Yeah.
increase kind of approach. So like, and then here, like I think that the essence is you are pruning this clean sequence, clean iteration for the least fixed point.
Right.
But we can, like one can also think about like trying to synthesize the ranking function itself from the.
Yeah, of course. Yeah, that is another approach.
Okay. Like, have you tried that or like?
Yeah, a student of mine is currently trying that.
Okay,
Yeah.
I see.
So you mentioned scalability to hundreds of lines of OCaml programs, and that's actually more impressive than it sounds, because OCaml tends to be much more succinct or functional languages tend to be more succinct. My question here is, what kind of challenge problems are you trying to tackle? Like, what would be like examples of programs where if you could do verification on them, using some of these techniques, if they scaled up, that would be like a big contribution to people using functional languages. Like, are there such challenges you see?
Well, I'm not sure. Yeah, so yeah, we are just picking the various OCaml programs in the GitHub and hope to verify the lack of assertion failures or pattern materials or like that. Yeah.
Yeah, I think some of these data structures, like functional data structures, might actually be good targets. Like, they tend to be very succinct and very complicated.
Right. Yeah, thanks. Yeah. If we have data structures, then maybe the tool probably will not scale even for a few hundreds. Yeah.
Okay, anything else? Otherwise, I propose we thank Naoki again. Thanks a lot for your wonderful talk.
Thank you.
So, thank you. So, This concludes the keynote talk. Enjoy the rest of the day.